Hola a todos. Bueno, empezamos la cuarta y última clase de esta semana. Anuncios no tengo por ahora, así que Laerte, todo tuyo.
Ok. La luz.
Sí.
Buenas tardes a todos. Today I will talk about deep learning. Deep learning is a very large topic, so we will focus on the main aspects of the field and on the main algorithm. Okay. Hmm. Let me tell you about the history of deep learning. Deep learning is based on neural networks. The first idea about neural networks appeared a long time ago, 1943, with an algorithm called perceptron. Perceptron is a very simple algorithm where, given a set of inputs, it produces a discrete output, either 0 or 1. The perceptron was implemented and demonstrated useful for, say, linearly separable problems. But in 1969 appears what is called the XOR problem. That in fact is a demonstration that the perceptron with the original architecture was unable to deal with problems not linearly separated. So the neural network field entered in what people calls a winter, a period during which nobody published too much on neural networks. Things began to change by 1986 with the appearance of backpropagation, that is a procedure for training neural networks. I will talk about it later. And at the same time, the neural networks appeared and started to many people start to work with it. In 1989, it was demonstrated the universal approximation theorem that says that with a single layer neural network, we are in principle able to emulate any function. 1992 is the date when the first paper using a neural network was published in Astronomy. We are here in another winter in the nomenclature of neural network, when there was not much funding for research in neural network because people realized that it was very difficult to train a proper neural network. By the end of this decade, people start to devise methods that separated the problems that was found during the first years of the neural network, basically by introducing new activation functions and better training procedures. It is 1997 that the IBM's computer Deep Blue beats Kasparov in the uh, in the game of chess. I was trying to. Okay. 1998 appears the convolutional neural networks. That is one of the most important and the most used architectures and we'll see later about it. By 2006, with the successive layer training, the problems of null gradients and the other things that were hampering the progress of the neural networks were separated and people developed very efficient procedures for training neural networks. By 2010, it started the usage of GPUs that are very important nowadays in the case of training and running very large neural networks. By this time, most of the methods of machine learning were like, say, random forest, SVM, were much more efficient than neural networks. Things start to change by 2012 when a neural network wants the ImageNet large-scale visual recognition challenge. This is a challenge involving many algorithms to identify a data set known as ImageNet. I will show it to you later. And then most of the important neural networks that we use today appeared in, say, the last 10 years, like variational autoencoders, generative adversarial networks. HasNet, for example, beats the human performance in many different problems. By 2017 appears what we call transformer, that is a game changer in the natural language processing. By a few years ago, Google produced the BERT, that is it's more or less incorporated in our cell phones. It's the algorithm that is responsible for suggesting the words for you when you are digitizing something in the cell phone. The same with GPT-3. That is a model for language processing that produces human-like text. It's amazing the kind of text that this algorithm can produce. And very recently, the visual transformer became to be applied also to images. This is just to show you that neural networks are actually a very recent algorithm in terms of the machine learning universe. Up to 2012, most of the most performing algorithms were those conventional machine learning algorithms. From this date on, the neural networks of the different types won all the challenges, and nowadays they are considered the best performing machine learning algorithms. Well, what are neural networks? It's an attempt to emulate what happens in the human brain. This structure corresponds to a large number of connected processing units that we call artificial neurons, and I will show. I'm showing here an example of an architecture of a neural network called multi-layer perceptron, where we have an input and artificial neurons between the input and the output. And each neural, artificial neural, it computes a very simple function. And during the training, we determine the weights between the connections between the neurons. It is in the weights that the information is contained in a neural network. What are the advantages of neural networks? They implement very easily nonlinearity, and in this sense, they can model very complex data. Its adaptability. They learn with the data. They are fault tolerant due to the distributed nature of the information. That's why we can work, for example, with missing data in many cases. And they implement intrinsically massive parallel processing. There are also disadvantages, like they are, in a certain sense, a black box. We don't know exactly what they do internally. There are problems on how to estimate errors with neural network, but all these points are subject to large efforts of research, and I suspect that is very few period of time they will be overcome. And an artificial neural network, like other models of machine learning, implements a function. And here I'm showing you the architecture of the first neural network used in astronomy, where the input is a series of galaxy parameters from the old ISO-LV catalog, like colors, profiles, measurements, elliptices, surface brightness, and the output was morphological types of galaxies, ellipticals, lenticulars, and so on. In the epoch, in the 1992, when this neural network was produced, its output, its performance was comparable to the best human specialists already. Since then, many other architectures appeared, and we can talk about shallow and deep, fully connected neural networks, or convolutional neural networks, recurrent autoencoders, and so on. Even in terms of learning, we can see different approaches, like the one used in supervised neural networks, like this one, which is an example of a multilayer perceptron. But we also have unsupervised neural networks, like the cohoning, and the others types of learning, like reinforcement learning or active learning, that is used in self-driven cars. And among the new activation functions that appeared to substitute the 0-1 output of the initial perceptron, we can include the sigmoid, the ReLU, and the linear. What are activation functions? These are indeed what each neuron computes. So, for example, in the case of the sigmoid, it receives an input x and produces an output f of x. The sigmoid has this form here. Its values are between 0 and 1. A game changer in this field was the introduction of the ReLU, rectified linear unit, that is represented here. It is 0 below 0, for example, or a given threshold, and a linear output for above this threshold. And we also use linear functions, mostly in the output in regression problems. Okay, let's look in more detail to the multilayer perceptron. That is one of the most used architectures for neural networks. Well, first, when we have here one input layer, an output layer, and in the middle, what we call hidden layers. When we have just one hidden layer, we say that we have a shallow, fully connected network. When we have more than one hidden layer, we have a deep, fully connected network. Fully connected because each layer, each neuron is connected to all the neurons of the following layer. Okay, you can see that this neuron is connected to the all neurons of the following layer. The inference is done in this way. We give an input and we compute the output. This is called the forward pass. In the case of the training, we compute a forward pass and then a back propagation pass that I will tell you about it soon. But this is one of the most common architectures that we find in this field. I will illustrate how a neural network of this type learns using a very simple example, the logistic regression that we have seen already yesterday. Let's now see logistic regression from the point of view of an artificial neural network. Let's suppose that I have an input and I want an output that is a binary classification. I will obtain a number between 0 and 1, where 0 is the class of a star and 1 corresponds to a galaxy. The input can be many things. In the case of star-galaxy classification, for example, it could be the colors and the other features of an object, like its width, things like that. In this example, I will use a sigmoid activation function. That's what logistic regression uses. And in this case, the probability that the object is a galaxy, y equal the probability that y equal 1 given x, is given by the sigmoid function as we have seen yesterday. In the case of two inputs, we can write the z that appears here in the sigmoid function has a linear form. So, given an input, the network computes the sigmoid function, producing a number between 0 and 1, which is interpreted as the probability of the object being a galaxy. The learning of this neural network is equivalent to the determination of the weights. In this case, we have 3 weights, W1, W1, W2, and a bias term, W0. How is done the training? Through gradient descent, as usual. We compute the gradient of the cost function, and it takes its minus sign, its negative value, in order to go towards the minimum. And one way of learning is the following. We can present an input to the network, it computes an output, and then we will adjust the values of the weights in order to decrease the error. This is called backpropagation. We first adjust the weights of the output layer, and then we propagate this error to the previous layer, and so on. So that's why the name backpropagation. We start from the first layer and go to the others. We compute the error in the output, then we propagate to the first hidden layer, to the second hidden layer, and so on, up to the input layer. Let's see how it works with logistic regression. Well, the output, as we have seen, is given by this expression. The cost function for a binary classification problem is the binary cross entropy that can be written in this way. T is the target. In the training set, we know whether an object is a star, 0, or a galaxy, 1. And y is the value which is the output of the logistic regression. So we can estimate the error of the classification of a given object in the training set using the binary cross entropy that is defined by this expression here. And the backpropagation involves the application, the direct application of the chain rule. So the derivative of the the cost function with respect to the parameters can be written as derivative with respect to y, derivative of y with respect to z, and derivative of z with respect to the parameters. Well, the first derivative, you can easily see that is given by this expression. The second term corresponds to this expression, and the third term to this expression. So, putting everything together, we obtain this expression for the gradient of the cost function. So, using the gradient descent approach, we can adjust the values of the weights after each data is present in this way, where alpha here is the learning rate. This is a very simple example of how backpropagation works. And this, of course, can be generalized to multi-layer networks, and indeed, gradient descent is used essentially in all types of neural networks that we work with. Okay, I have mentioned the universal approximation theorem. This is very interesting. It can be demonstrated that any continuous function can be represented by a neural network with a single hidden layer. But you know, in general, we don't use a network with a single hidden layer. We use several hidden layers, which that means that we use deep neural networks instead of shallow networks. And why this happens? Because it was demonstrated that it is very difficult for a single layer network to learn the function. And it is much easier to do it with many hidden layers. That's why we use nowadays deep networks. It's interesting that any function can be represented in this way, and this is one of the strengths of neural networks. Well, we need, in all problems of this kind, to define the loss function or cost function that we will use, and there are many different problems. For example, we can have a binary classification, or we can have multi-class classification with a single target, or we can have a multi-class classification with multiple targets, or we can have regression. And for each of these type of problem, we have different cost functions. So for a given type of problem, we need to choose the appropriate cost function. Okay, one very important type of neural network are the convolutional neural networks. And they revolutionize the analysis of image. You can imagine how difficult for an algorithm is to recognize image. Mostly, if we think about this problem in terms of classical computation, you should, classical computation involves we posing several different rules. But this is almost impossible for a problem like image classification, because, for example, here are all galaxies, and we can see how different each image is from the other. Another problem, segmentation. Segmentation in image analysis corresponds to the identification of the pixels that associate to a given object. And for example, if we run Sextractor in this image here, it can consider, for example, that this H2 region here is a different object, when in reality it's part of the same of this galaxy. So objects can be broken in several pieces, and this is a difficulty with also with conventional methods. Invariance. For us humans, it is easy to identify an object that is in a position or is inclined or rotated, etc., but not necessarily for an algorithm. And the deformations. For example, we have here many examples of handwritten digits, and you can see how different each the same digit can be. And in fact, the convolutional neural networks were introduced to overcome all these problems. They were introduced in 1998 by Lecan, and although it is used mainly with images, they can be used also with vectors and the other kind of data. There's a basic difference with respect to the multi-layer perceptron, because in this case, the connection between the layers is local instead of what happens with the densely connected multi-layer perceptron. So, for example, we have an image here, and what the CNNs do is to run along the image and estimate numbers in each piece of the image. These detectors actually implement what we call filters. I will show an example soon. So, in a convolutional layer, each hidden unit connects to a small region of the image, sharing the same weights. Each layer has many filters. So, for example, here are different pieces of the image that are shared by the network. So, here is an example of a kind of filter. I have an input image. If I pass a filter like that on the image, this is the kind of output map that we obtain. In the case of neural networks, during the train, many filters are learned, as you can see in this image which represent the filters in the first convolutional layer of a very popular CNN algorithm proposed by Krzyzewski. What is the architecture of a CNN? A CNN is a pile of what we call convolutional layers and pooling layers. For example, the convolutional layers implement this pass over the image that I have just talked about. The number of filters will depend on the depth of the output volume. For example, the height and width of each filter that will being passed over the image. The pass or stride is the separation between these filters. So you can see that we can have lots of different hyperparameters here. Huh? The pooling layer is the following: when we pass all the filters of the image, we obtain, say, something like this. The problem is that the amount of data can become enormous. So the role of the pooling layer is to reduce the dimension of the previous layer. For example, we can consider a part of the image and take either the maximum or the mean of each part, and this is what the pooling layer does. So, for example, in this case, we take the maximum value here, the maximum value here, and with that procedure, we reduce the size of the neural network. Because neural networks of this type, convolutional neural networks, have a huge number of parameters due to the weights connecting the several layers. Here is an example of an architecture where we have 60 million parameters. It is not unusual that a CNN network has thousands or even millions of parameters. This is very common. And this procedure of using convolutional and pooling layers that allows the network to learn. So the structure is more or less like that. We have an input layer, convolutional layer, pooling layer, and so on. And we repeat up to the end. So we present an image here, and in the end we obtain a classification here. For example, in this case, a cat. The training of a network like that, although its architecture is completely different of a multi-layer perceptron, is also a kind of backpropagation, gradient descent. A very interesting thing about neural networks is the following. And I'm presenting this here because we very often, when we work with CNNs, we use pre-trained CNNs. What is a pre-trained CNN? We can say train a neural network using an image database like this one I'm showing here, called ImageNet, which is a database that contains 14 million images classified in 1,000 categories. So, for example, we can use a network of this kind applied to ImageNet, this database here. And what we do is the following. We use the pre-trained CNN here, and we add to the CNN a multi-layer perceptron. That means a fully connected network that then produces either the classification or the regression that we are using. What is the motivation of doing this sort of thing? Is that the idea is that being trained with such a large amount of images, the network will learn a lot of interesting filters that might be useful for other problems involving images that are not here in the ImageNet. So it's very common, for example, if we are developing a project for galaxy classification using images, to use pre-trained CNN, and where we add a multi-layer perceptron and then do the classification or the regression that we are trying to solve. And this type, this network, for example, is called the VGG16, and it was the winner of the ImageNet competition in 2014, and it's very useful for us because we use its core, and we add the multi-layer perceptron. Then instead of using the ImageNet data, we train only the weights of the multi-layer perceptron to, say, classify galaxies. This part of the network, we frozen the weights. We don't train at all. So this is a very powerful way of training a CNN and obtaining interesting results with CNN. This is a type of what we call transfer learning, knowledge transfer from a net to another. This net was used to classify objects like cars, cats, dogs, etc. And we use we use its structure to classify galaxies, for example. Well, one problem with neural networks, since it has such a large number of parameters, is overfitting. I have shown you how to monitor the cost function to verify whether the net is overfitting or not. And in general, one can adopt some strategies to reduce or avoiding overfitting. In the case of CNNs, two are more important. One is data augmentation, the other is dropout. Data augmentation means that we can enlarge the training set with image variants like reflection of the image, translation, rotation, distortion of the image. This is a very useful technique. The other approach is what we call dropout. One can include a dropout layer before the fully connected network. And what a dropout does is that it removes randomly inputs from the multi-layer perceptron that follows the CNN. Instead of using all the inputs, we randomly select, say, 70% only of the inputs, and we use it in the training phase. This is a very powerful procedure to avoid overfitting. Well, another important type of neural network I have already mentioned to you is the autoencoders, and which have an architecture of this type. What characterizes the autoencoders is that it is trained such that the output is equal to the input. But since we have a reduction of the number of the nodes in the middle of the network, this implies that in order to learn the output, the autoencoder needs to learn how to compress the input. The nodes here implement what we call the latent space of the data. One very important variation of the autoencoders is what we call the variational autoencoders. Instead of learning fixed values in the latent space, we represented the latent space by statistical distributions. So, for example, each node here learns a mean and a variance. And this implies that we are able to incorporate statistical fluctuations, statistical variations in the own architecture of the autoencoder. This is a very powerful technique used for example, for image generation. Here's an example where we can train a network to recognize images with this type of architecture, but instead of fixing the fixing values here, the network will learn the mean vectors and the standard deviation vectors, so that they can sample from the latent space and produce an output that is statistically more robust than just keeping fixed the weights in the middle of the autoencoder. this type of autoencoder is very useful to generating, say, fake images. Most of the images that we see, I think that all of you have already seen that images of persons that are not real. These are produced either by variational autoencoders or by what we call GANs, Generative Adversarial Networks. I put here this sentence of Chollet's book because I think that it explains very well how a generative organ works, generative adversarial networks, how it works. Let's suppose that we have known a forger that is trying to create fake Picasso's paintings. At first, the forger is pretty bad at the task. He mixes some of his fakes with authentic Picasso's and shows them then all to an art dealer. The art dealer makes an authenticity assessment for each painting and gives the forger feedback about what makes a Picasso look like a Picasso. The forger goes back to his study and prepares some new fakes. As time goes on, the forger becomes increasingly competent at imitating the style of Picasso, and the art dealer becomes increasingly expert at spotting fakes. In the end, they have on their hands some excellent fake Picassos. And this is what is around the GANs. For example, if you look at the site here, this person does not exist, is many images of persons generated using GANs. GANs have two parts, the generator and the discriminator. The generator takes a random point in the latent space and it outputs a synthetic image, and the discriminator or the adversary, and this is linked to the name of the algorithm, takes as input an image, real or synthetic, and predicts whether it's real or synthetic, real or fake. It implements a classifier. The generator is trained to be able to fool the discriminator and thus evolves to produce increasingly realistic images. The discriminator is constantly adapting to the improving capabilities of the generator. Once trained, the generator maps any point of its latent space into a believable image. This is one of the most known softwares for generating fake images, and not only fake images, we can use it to, say, simulate galaxy models, disk around black holes models, things like that. Well, although this seems very complicated, I can assure you that after a bit of experience with this kind of algorithms, things become very clear, and they are not complicated at all, and they are not difficult to implement at all. Chollet, who is the author of my Bible, I will soon show his book to you. He presents what he calls the universal workflow of machine learning. I have already talked about it yesterday, but now I will mention it in the context of deep learning. Deep learning works better with normalized features, either between 0 and 1 or by the subtraction of the mean and division by the standard deviation. That's it. If you want to train a neural network, we need to normalize the input, either between 0 or 1 or through standardization. In the case of this sort of neural networks, the more examples, the better. So data augmentation is a very good procedure to implement more elements in the training set. In the case of classification, we should always use balanced samples. Otherwise, we'll bias towards the most populated class. In deep learning, the more layers, the better. And Cholet suggests the following. First, create a network complex enough to overfit, and after, simplify it or add regularization or dropouts to avoid overfitting. If your sample is small, use a pre-trained network or train your sample on a large data set, like ImageNet, and then train with your data. Well, I have mentioned a few types of the neural networks, but there is a universe of algorithms here. So these networks, the multilayer perception, which are the fully connected feed-forward networks, are one of the most popular. In the same way as convolutional neural networks. Autoencoders, either simple or variational or sparse, another type of autoencoders, are also very useful. GANs, what we call Bayesian networks that are interesting algorithms because they are able to produce errors for the outputs. UNet, recurrent networks that are useful in, for example, in the analysis of time series or in the natural language processing. LSTM, long short-term memory, also useful for time series and the natural language processing. Boltzmann machines, Cohone networks, transformers. Well, there's a big fauna. Even today, I learn about another type of neural network that I never had known before, called the Fourier neural network. That is some are very useful to emulate differential equations, and people are using it to simulate, say, hydrodynamic equation. Okay, I would like to finish by suggesting you two books. This, the second one, Deep Learning, is the Bible and was written by the saints of the deep neural network religion that are Goodfellow, Benjo, and Curville. This book is excellent. It presents all the formalism behind the algorithms. We don't need to know these details, but if you want to know, this is the place to go. And the book is available in many different languages at this site. And in my Bible is this book, Deep Learning with Python. The author is François Cholet. It is also available in the site, and all the programs are available also, not only the discussion of the theory about the models. And my suggestion is, if you want to learn how to do deep learning, this is the book to look at, because I find this book excellent, and it has all the codes. If you have a problem, you first run the codes corresponding that are able to be solved, that are able to be used for your problem, and then change the pieces of the code in order to use your own data instead of the examples present in the book. I think that's what I would like to tell you today. And Vitor now can present more practically the examples that we are considering here.
Questions?
Hello.
Yes.
Is there a relation between the number of images in the training set with the weights that the network needs to learn? I mean, how can I choose the size of my training set?
Well, the larger the better. The point is, no, there's not a relation, but since the number of weights can be very, very large, if you have very few examples in training set, you will be unable to properly train your
Yeah.
network. There are procedures to deal with problems where you don't have a very large number of data. No, you can do data augmentation, for example, or use other types of networks that I didn't mention here, like active learning, for example, that are able to learn with a fewer number of examples. But in general, the rule is the largest training set, the better.
Thank you.
And, when you said that it's better to normalize the features between 0, 1, or subtract the mean and divide by the standard deviation. In this second case, suppose we are working with images, yes? The mean would be, I imagine the image as a array of pixels, right? So the mean, you think for each pixel, I mean, what would be the mean and what would be the standard deviation? The mean for all the images, the mean in each pixel, and the standard deviation in each pixel, or you would produce the mean of all the image?
No, it is for each
pixel.
feature. If each feature is each pixel in the image is for each pixel, not for the image as a whole.
Okay. And then another question about the activation function, because you explained that with a single layer, but then you move to, in the case you have several layers, and you at some point it said the activation function in the last layer, but I suppose the activation function is at different layers, at all the layers, no? Because the neurons are activated with the same activation function. Is that the case?
Sorry, I didn't understand.
No, because I was following your explanation, and you introduced the activation function when you were discussing the case of only one layer, and then you introduced the case of several layers, and in the slide it mentioned the activation function if the last layer was sigmoid or whatever, and so I thought the activation function is the same at when you have multiple layers. The activation function in the architecture is always the same.
You can. This is an engineering problem. You can use all the same activation function in all the layers, or you can in a given layer you can use sigmoid, in the other one ReLU. But in general, nowadays we are using much more ReLU than other activation functions because the neural network learns faster. The important point regarding activation functions is that they should implement nonlinear functions. And both sigmoid and ReLU implement nonlinear functions. ReLU also is better for convergence, and it was one of the ways to overcome a problem that we had at the beginning when working with neural networks. That was the following. I personally had this experience. If you have several different layers, the network entered in what we call zero gradient, and it was unable to learn. This was changed later with better algorithms and with the introduction of ReLU. So in general, if you, I don't know what activations are you are going to use. Yeah, Vitor, for example, in the examples that he's going to show you, uses only ReLU. But you can also use sigmoid. But you verify that it will take more to train, and maybe the results are not so good. Anyway, in the case of problems with regression, the last layer should be a linear layer, because regression is a problem where we have a continuous output, and the values that the function should have in the output may cover a large range, not 0 and 1. So we use linear activation layers only in the output of regression networks. I don't know if I answered your question, but
broad question and broad answer, it's fine.
yeah, notice that this is a kind of you need to experiment in order to find the best thing to do with your network.
More questions? I have a question, but perhaps it is better to leave it for the end. No, because I would like if you can tell us more about these challenges, these deep learning challenges.
Okay.
I
don't know if you know the Kaggle site.
No.
It's a very important group of people that every year they present a problem, and anyone can participate. And they give you a data set and what they want. For example, they give you the ImageNet set, millions of images, and you enter with your algorithm and try to win. And for example, the ImageNet is now considered overcome because the kind of neural network that I have shown to you, it achieves already 99% of accuracy in the classification of ImageNet projects. But all the time, people are proposing new problems, and every year there is a competition. I suspect that the Kaggle is supported by Google, and because in the site of Kaggle there's the logo of Google, but I don't know who is behind it. But it's one of the most important sites for people working with machine learning in general. And that's in this way we can see how different algorithms are being used by the community, what kind of algorithms are performing better. So this is a very interesting site because you learn a lot about the sociology of the field just looking at what kind of algorithms and computational languages are being used. It's very interesting.
And anyone can participate, you said?
Yes.
And is there any registration or?
Yes, you need to register. If you Google Kaggle, Kaggle, you'll find it.
Okay.
I recommend to everyone, including because there in the site there are all the codes of the programs. So instead of inventing a new program, you can get one of the best performing codes and adapt to your work. Mm-hmm. This is a big advantage of this sort of algorithms nowadays, because when I did my PhD, I need to do everything from scratch in Fortran. Okay, but nowadays things are a bit easier in this sense. You need to focus your intellectual effort more in the problem itself than in the hard work behind the program, things like that. And if you look at the book of Cholet, as I mentioned to you, the programs are there. You can just copy it, run what Cholet, first with the data that Cholet provides, and to see how things goes, and then change for your data. It's very easy to work nowadays with deep learning. This is my and another interesting point. You see, there are thousands or millions of parameters in a typical deep learning algorithm, but it in general it runs much faster than other conventional machine learning algorithms like a random forest or support vector machine. In general, I use deep learning because I don't have patience to let us say random forest finish running because it takes a lot of time more than a typical deep learning algorithm. People worked a lot in the keras, in these packages that we use to run deep learning, and the algorithms are very, very efficient, much more efficient than the other machine learning algorithms. This is my personal impression. Huh?
Thanks, Laerte. More questions?
Another question that I have, another doubt, is when you show the augmentation procedure to generate more images to train by rotating or even distorting the images, it came to my mind the case of the weak lensing, for example, if I was looking at images of galaxies, and there will be a physical effect, which is weak lensing, in which galaxies are distorted for this effect. So if in my network I train with images that I'm artificially distorting them, wouldn't I be leading the network to learn something which is not, I don't know if I'm very clear with what I'm saying, but if I distort artificially the images, wouldn't be showing the network something which is unnatural, in the sense that the network will learn that the images are more distorted than what they are in reality?
Well, you can train a network in the following way. You can produce artificial images, for example, with an image without lensing at all, and the other with lensing. And you can then apply real images to the network, and it produces the unlensed images. Or the output could be the mass of the cluster that produces that distortion. I don't know exactly if it is if what you asked me, but
no, because I was thinking about training with real data. If you want to train with real data, I don't know.
Yes, but okay. There are competitions among the in astronomy to, for example, to people working with weak lensing in order to estimate the properties of clusters, things like that, using weak lensing and outputting the properties of a cluster, say cluster mass, things like that. In this case, you train the network with artificial images, but after you apply to real images. I don't know if this answers your question or not.
Yeah, well, but my question was, what happened with this augmentation of images? You are generating more, not only rotating the images, but also distorting the images. So when you distort the image, you are distorting the shape of the galaxies, and you would be introducing a fake weak lensing on
No,
those galaxies.
I see. But not necessarily all these types of data augmentation are used for all types of problems. You need to have this in mind also. Maybe for weak length studies, this kind of distortion that people apply to cats doesn't apply to galaxies. But
More questions?
I
Okay.
encourage you to try deep learning using these books because it's very easy. It's not difficult. And you should make a group of people and start learning the book from the first chapter, reproducing the examples, and you become experts in the field, able to produce, obtaining results, good results for the problems that you are interested on.
Thanks a lot, Laerte.
Hi, so this is Vitor again. I'm going to go through the last notebook that I want to show you. And yeah, so today we're going to talk about the big topic of deep learning. And so I try to pick the two things that I think are most important when starting with deep learning, which is convolutional neural networks and the feed-forward neural networks. Basically, the case of convolution, we're going to talk about images, and in the case of feed-forward, we're going to talk about regression. Bayesian for classification, but like basically non-image data. So the first thing that I want to talk about is that Laerte already mentioned before, is that GPUs are very important when using deep learning because they make things much faster. The idea of connecting the neurons are basically like matrix multiplication. So doing that in a GPU, it's much faster. So you can actually change, even though we are running in Google computers, you can actually change the hardware we are using to run the code here in Colab. So just click on runtime, go to change runtime type, and there will be three options: none, which is CPU, GPU, and TPU. TPU is a kind of new software that is being developed, I think, mainly by Google, which is, I think it's called Tensor Processing Unit, which is kind of like a hardware specifically created to use machine learning to run like high level codes, and but we don't need GPUs right now. We just need GPUs. It's enough. So if you run this notebook on CPU, I think some codes will take like 10-15 minutes to run on CPU, and in GPU it takes like some seconds. So okay, so let's start. So I want to first talk about convolutional neural networks, and as Laerte presented before, it's going to be network designed to tackle high dimensionality problems. So things like images that you have like a matrix of data for each observation. And so the main applications are in computer vision, and they can be used for, but not only for computer vision. I want to be clear that, for example, there are some studies that are trying to, I think we reviewed a paper some weeks ago that was using convolutional neural networks to obtain photometric redshift, and so from the spectrum. And so anything that you have a lot of data for the input, you can maybe try to use convolutional neural networks. So here I'll try to give you an example by using MNIST, the MNIST dataset, the one that we used yesterday. that is the handwritten digits. So basically what we try to do is do the same type of solve the same type of problem, which is classifying the handwritten digits through the neural network. So for most of the machine learning problems, we use the sklearn library. So the sklearn library contained most of the SVM, I think random forest, even XGBoost you can find inside sklearn. But now with deep learning, there are mostly two very big libraries. So one of them is the TensorFlow, which has a sub-library called Keras, which is the book the Laerte presented before. So the François Chollet, which is the writer of the book, is one of the creators of the Keras library. And the other deep learning package, which is very big, is the PyTorch. So PyTorch is another Python deep learning package, and each one of them has its advantage. So the simpler one is Keras, which is the one that we're going to use today. So it's the easiest one to see, to work with, but PyTorch and TensorFlow itself have some advantages, like the ability to control more the parameters and what's going on inside the network. And so, okay, so just to, that's why you're going to see a lot of TensorFlow and Keras throughout the code. So let's, the first part to do this problem is to download the MNIST set, and we're going to, this is just a reuse of the code that I wrote yesterday. So I'm going to download the same way. We're going to download the MNIST dataset, which again is for I think 70,000 or 6,000, I don't remember correctly, images of the handwritten digits. And let's see some of the images just to see what we're working with. So it's the the handwritten digits, and in a 28 by 28 pixels each one, and each value, each pixel goes from 0 to 255. And now that we're talking about convolutional neural networks, you can start working. So you had a kind of a problem when you worked with like random forest and classical machine learning libraries that I told you yesterday. That was, you needed to convert your matrix, like your image, into a 1D array, because you couldn't give a matrix to the model. And now that we're working with convolutional neural networks, they have so much capability of like making these matrix convolutions, that you can actually work with images with colors too. So you can, instead of just having a single value for each pixel, you can have, for example, an array of values. So like 3 numbers, usually the RGB numbers of the image. And so this is one of the big advantages of the convolutional neural networks. So since we have this data over here, let's try to, the usual workflow is to usually reshape the data first. But since we don't need to reshape, you can just pass the 28 by 28 images to the network. Let's just normalize the data. So we'll just, since all of the maximum value of each pixel is 255, if you divide every one of them by 255, you just end up with a number between 0 and 1. So that's how we're going to do the normalization. And then we need to convert our targets or labels of the images. So remember that each image, each one of those images has a specific label related to that image that goes from 0 to up to 9. So representing the number that is described in the image. And now to work with convolutional neural networks, instead of outputting a single value, a single number that goes from 0 to 9, what you're going to do is work with what we call a one-hot encoding. It's basically just a transformation. So instead of giving a number between 0 to 9, we're going to utilize a matrix. So let's say, for example, that we have a data set with 3 images. Let's say they have the classes cat, cat, and dog in this respective order. Then we could represent those targets as the following matrix. So we have a matrix over here that has 1, 0, 1, 0, and 0, 1. Each line represents a different image, a different prediction by the network, for example. and each column represents the class that it's on. So the first class, the first column represents, for example, the cat class, and the second column represents the dog. So it's saying just the first image, the first line is being represented by a cat, and the second being represented by a cat, and the third one by a dog. So this is an important step with convolutional neural networks, because their output is usually it works better when the output is in binary numbers in this way, in a matrix way. Okay, so how we're going to do that is we're going to use and again, just to tell you that if you see this expression in the documentation, one hot encoding means this. So transform your linear data into categorical data. And so we do have a function in Keras that helps us do that. And to transform the train the targets into a categorical data, do the one hot encoding, we just use this function over here, the to categorical, from the keras.utils library, and we just tell it what is the data that we are classifying and the number of classes that it has. So in this case, 10 classes that are going to do exactly that. It's going to create this matrix over here. Okay, so let's now build, since we're done with the shaping the data, transforming the data, and making sure that it's good for a model to read, let's try to create the model itself. And remember that this is all part of the like universal workflow of machine learning. You first treat the data, and then you create the model, and then you feed the model, and then you try to analyze the results. And okay, so let's start with the model. We're going to create a simple convolutional neural network. So a convolutional neural network, as Laerte presented before, is basically defined by having a convolutional layers, and each one of those layers, so we create a simple network with just two convolutional layers. And so they have a conv2d, and then followed by a max pooling layer, and the max pooling layer is trying to break down the image. It's going to apply something like a dimensionality reduction function. So it's going to, I think each max pooling layer, Laerte can correct me, but I think they break down half of the parameters just to make things easier for the network. Since if you try to only use convolutional layers, it's going to make the parameters, it's going to create a lot of parameters. And it's going to be hard for the network to estimate. It's going to take a long time. Okay, so let's create our model. So it's going to be a Keras sequential model, which means that there are a number of different ways that you can create your model. So one of them is sequential, which is basically like the images that we usually see, that Laerte presented, which is one layer after the other. So the connections from one layer is solely based on the layer before, the layer behind it, let's call it. And so there are other types of networks that are not sequential, that are kind of so one layer is connecting to the one in front of it and the one after it, or like whatever connections you want to create. But this, we're going to use a sequential layer, a sequential model, which is pretty kind of simple. So the input shape, so the first thing that we need to create is the input layer. And the layer is going to be, we need to tell its shape. So in this case, it's going to be a 28 by 28 image. And there is a 1 over here just saying that is like each pixel has only one value. So if you had a 3D image, for example, you could change its value to 3. Oh, sorry, not a 3D image, but a colored image. You could change its value to 3 to represent the RGB numbers. And next, it will be followed by a convolutional 2D layer, which usually in cases of using a sequential layer, usually we start with a number of parameters like 32, and then we go the next layer, we have like 64. Usually increase the number of neurons in each convolutional 2D because of the max pooling. And so after doing that, after having two convolutional layers, we have a flattened layer. So it's basically going to, oh, sorry, I didn't mean to cut this off. Sorry. And then we're going to have a flattened layer to make this, instead of having a matrix, we're going to have just a 1D array of neurons. Then we're going to have a dropout layer, which is going to make all of the 50% of the data go to 0. And finally, we're going to have a dense layer, which is going to make the classification with a softmax activation. And you can see here that I think, as you asked before, so each layer has its own, each activation layer has its own activation function. And you can see, for example, the max pooling, which is not an activation layer, doesn't have an activation function. Okay, I know that's a lot of information, and it's quite hard to like absorb it all. But this is the usual way that you're going to see convolution in neural networks. It's always a convolutional layer followed by a max pooling layer in how many times you want that combination. And then you're going to see a flattening layer and maybe some dropout layer, and then you're going to see a final dense layer that's going to create the classification itself. And you can use and this is the way that there are two ways mainly two ways that I've seen normally to actually create the models with Keras, with the Python library. One of them is by using the Keras sequential and then just typing down the layers itself. Another way that I'm going to show later for the next case is to initialize the Keras sequential and then adding layers one by one, which is mostly the usual way. But I think it will be clear when I show the other type. But basically, there are a number of different ways for you to actually create the code itself. And after placing this bunch of code over here, you can see like a summary of the model just to see how it looks. So it's going to look like this, the summary. So it's just saying what it has. So I think there is a okay, so the convolution to the layer followed by a max pooling, following another convolution, then another max pooling, then flatten, then a dense. It's because I forgot to uncomment the dropout, but if I commented it in, there will be a dropout layer over here. Okay. So I think that mostly at least kind of shows you what is the first time like looking at it. And this is just creating this function over here. It's just kind of creating the function in the first time. So you're just stacking layers together. Now you need to kind of compile the layers together, and that's going to be done by this compile function over here. So you call your model, and then you write down .compile. This is going to just like glue everything together. That's the idea. You first stack the layers and then you compile the model. After you compile, you cannot make any changes. For example, you cannot add more layers or remove layers or anything like that. Your model is set and is ready to be trained. So and there are a lot of metrics. So let me go through it a little bit. So in the compile, when you compile a model, you're going to choose the loss of the model, which in this case is going to be a categorical cross entropy. So it's basically a cross entropy that's going to be it's created to be used for categorical models. And we're going to use an optimizer, which is called Adam. Laerte mentioned it briefly in the last class, because I'm not sure if you can use this optimizer in other kind of machine learning examples, but when using deep learning itself, the Adam optimizer is one of the best. So it's a very good optimizer, and usually are going to use Adam itself. And then you can define some metrics for your model to output. So even though, for example, the categorical cross entropy will be the loss of the model, which, if you remember from the class, it's the thing that we're trying to lower. So the loss, we want it to lower it as much as possible. The metrics are just going to be something that the network is going to calculate and can be a more digestible metric for you to understand what is going on. So in this case, for example, we're going to use the accuracy, and the accuracy is a very simple metric for us to understand. It's basically the rate of the model itself is managing to get correct. the amount of data that is managed to get correct. Okay, so there is so after compiling and also there are a lot of different things you can do with those parameters. So the loss, the optimizer, the metrics, you can change it a lot. And if you go to the, I always recommend it, but I will recommend again. If you go to the documentation of Keras, when there is a lot of different. If you search, for example, for the compile um, method from the sequential neural networks, you see that they have everything explained. So they have all of the different losses, all of the different optimizers, all of the different metrics, and you don't need, for example, to use a loss that is preset. If you have like a different problem that you want to create your own loss, for example, in the case of Bayesian neural networks, you can actually just pass a function. So there is a lot of things you can change here, and I really do recommend that you change some of that and see the results, see how it goes, see what works, what doesn't work. And after compiling the model, you can fit and train your model. So in this case, we just again, as just like the other machine learning codes that we used before, we just going to use the model.add fit function. So we're going to give it the training, the training set, sorry, the features and the targets. And again, we have a lot of different parameters that we can change, the hyperparameters. And in this case, these are usually what we're going to want to change to train the network with. So we're going to change the batch size, we're going to change the epochs, we're going to change the validation split, for example, or whatever we want. And each change, for example, if we change the batch size, it's going to give a different result. If we change the epochs, it's going to change it to give you a different result. Let me just change to 7 RAM since I don't intend to run anything. And the batch, just to explain the ones that I wrote over here. So the epochs are going to give you an idea of how long the model will train. So in this case, it will train for 15 epochs. It will train for 15 iterations of the model. The batch size is the amount of data you will try to get like at a single time. So in this case, it's going to take like 120 images at the same time, and then you're going to analyze those images and try to get a graph of the loss of those images. And then it's going to take another batch of 128 images and finish all of the data sets. Also, it's going through like different batches of 128 images. And you can change this batch size, for example. You can change for a lower value, like 1, for example, but you take a much longer time for you to train your network. So you want to kind of have like the sweet spot where you have like a batch size that is large enough that you can run your network fast, but it's not small enough that you don't lose, like, for example, some like your loss don't go too bad. Your results aren't like get worse because of it. Okay, so after calling this method, you usually see something like this. So Keras outputs, like each training, each epoch is going to show you like this this bar over here that's going to go from left to right, like a loading bar. It's going to show you the time it took to run the network. It's going to show you like the amount of time it's taking for each one of the calculations, the loss of the network, the accuracy, and it's going to also show you the validation loss and then validation accuracy. So it's the same loss and accuracy, but applied to the validation set instead of the training test. This is for training, this is for validation. And usually what we want to do is to take all of this data. You're not supposed to like look at it and like try to write it down or anything like that. It's always stored inside Keras. So when we finish the training, it's going to, you can see that for this one, it took like 3 seconds per layer, sorry, per iteration, per epoch. So it was quite fast. And then we're going to like evaluate the trained model by using any of the metrics that we used before. So in the case of the like what we did before with the metric, sorry, the machine learning codes like random forest and XGBoost, you can see that it's the same idea behind it. So you can predict new values from the a model.predict function. So for example, I can take the training test and pass it through over here, and you will try to predict a new the values. But what I can also do is just use a evaluate function from Keras, which is basically this evaluate function is going to take an original like a data set, and then it's going to take like the targets of the model, which is the labels of the images, and it's going to give me both the test loss and the accuracy, which are the metrics that I'm using before. So it's are the same metrics that I defined over here. If I inputted more metrics, for example, the score will give me more metrics, like the error, the general error, or the F score, for example. And we can see that in this case, the accuracy of the model is like 99%. So the model is managing to, even though it's a very simple convolutional neural network, is managing to classify the images very well. So it has a very good grasp of the MNIST and how to classify numbers and things like that. And so I think that's what I wanted to show you from like image processing, because convolutional neural networks is a very extensive field, and there are a lot more things you can do. There are Laerte mentioned before, you can use, for example, pre-trained models from like those challenges, for example, the VGG or the ResNet 50, which are the ones that are very famous models. And you can try to do that. For example, if you have a project right now that you want to classify stars and galaxies, you can try to use that. I think I linked at the end some links to for you to manage to look at how to use those pre-trained models. Okay, so now we're going to move forward and talk about feed-forward neural networks. We're going to change the subject. Instead of talking about images, I'm now going to talk about like some like classic data, which are like some tabular data. And okay, so despite of the complex name, feed-forward neural networks are the most common type of network you will see. So they are the basis, for example, for autoencoders, for a lot of different things. And so this represents most of the networks that have an architecture such as this one over here. So let me zoom out, okay, just so you can see the home image. And you usually have something like this. So this, for example, is one example of a feed-forward neural network. So it has an input layer, which it will be in the size of the features that you will want to give. So for example, in this case, we're going to use the S plus data. It's the same data that we used in the yesterday's class. So we're going to use some S plus data. So it will be, for example, the 12 magnitudes of S plus a value of redshift. This will be the shape of the input layer. And each node over here is going to take a different one of those features. And that is going to go through multiple hidden layers. So this can be how many hidden layers you want. You can input, for example, some dropout. It doesn't need all to be activation layers. There can be some like dropout layers in the middle. You can mix and match with a lot of things. And at the end, after going through so these layers over here, the hidden layers, are the ones that are actually going to do the hard work. So these are the ones that are going to like make the calculations and try to actually find the relationship that you want. And at the end, you have an output layer, which will be in the shape of the value that you want. For example, in this case, we're solving a regression problem. So we're just going to have a single node that's going to output one single value, which is going to be the stellar mass of the galaxies. And so, but for example, if you wanted to estimate different values, you could have like an output layer with a different shape than one. Okay, so let me zoom back in. And so these networks, so they usually I'm just describing how they like the input, the hidden layers, and then the output, and they can be used for regression, classification, for dimensionality reduction, and many other classes. So let's see how to actually implement one of them. And in this case, we're going to, again, just to reinforce that we're going to use the same data that we used yesterday, which are the magnitudes of S plus versus the plus a value of redshifts, and we want to compute the stellar mass. So just to look at the data after downloading it, it's the same code that I used yesterday, the same Dropbox link, for example. We're just going to read the data, and then we're going to see that so each one of those columns is a different filter from S plus, so it's basically a different magnitude. And then we have a value of redshift, which is the Z, and then we're going to have the log mass, which is the stellar mass of the galaxy. Okay, so we want to make the regression problem that we want to solve is to use all of this data over here to regress into this log mass. Okay, so let's see how to actually do that. And again, let's go back to the universal workflow of machine learning that Laerte presented before. You usually you first want to work with the data and then build your model, then fit your model, and then analyze the results. So the first thing that we're going to do is to see the data, to work with it. So in this case, we're going to just split the data between the that we want. So we're taking the every single column, but the log mass. So we're dropping the log mass as the features, the data to be trained, and then we're going to be used as a target the log mass. And then I define the test size and the training size the same way that I did yesterday. It's 15% for the testing and 85% for training. Okay, so now we're going to scale the data, and I don't remember if yesterday I used min-max scaler, but I think I did. But you can use the standard scaler, for example, which, if I'm not mistaken, is going to do what Laerte told before, which is like it's going to subtract the mean and then divide by the standard deviation. And so, but I'm going to use min-max scaler. Is just basically going to compress the data into a 0 to 1 range. And we're going to define a x scalar and a y scalar. Again, we need to fit all of these I talked yesterday, but we just need to fit the data to the training. So we use the scalar just to fit the training sample, and we're going to apply the scalar to the testing set. Also, we're going to fit the training set and transform it already into a 0-1 range, and we are also going to do that with the labels, the stellar mass, and then we're going to transform the test set, the test data set, based on the scalar that was obtained by the training set. Okay, so now let's create the feed-forward neural network itself. So we're going to apply the same concept we did with the CNN. So we're first going to stack the layers. We're going to define the layers that we want. Then we're going to compile the model, and then we are going to fit the data. So I'm going to do what I'm going to do now is to create a build model function. So I'm just going to put all of that information inside a function over here, because in later steps of the notebook, I'm going to do some hyperparameter optimization and making so it's a function instead of defining the models each time is going to make our lives is going to make things very quicker and easier to read. But it's the same idea. So we're going to define a build network model, which is going to take some data, it's going to take some training data, it's going to take some layers, it's going to take some neurons, and then it's going to go through the. So let's see how it works. So the first thing that we need to do is to define the type of model that we're working with. And in the same case, we're going to use sequential. Again, sequential will be the most the model, the type of model that you're most likely to use, because sequential is the easiest one to use. You just need to stack layers together. You don't need to think about different layers interacting with one another. Okay, so let's input the first layer. So in this case, since I'm defining the sequential layer over here and using the model variable, I'm going to start to add layers to this model. So the first layer that I'm going to add is the input layer, which is going to take which is a dense layer with it has a number of neurons And then we're going to the input shape, which is the, oh, sorry, this is not the input layer. I'm sorry. This is the the very first layer of the network. It's this one over here. The input layer is going to be already defined by Keras by using this input shape. So it's basically the one before that. It's going to have the same shape as my training set. So it's going to take the features from my training set. So in this case, we'll have 13 features, which are the 12 magnitudes plus a value of redshift. And then we're going to go through the other hidden layers, the additional hidden layers. So we already have one defined, which will have a number of neurons that will be also passed. In the default case, it's going to be 128. And then we're going to go through the hidden layers. In this case, if you have, for example, 2 hidden layers, one is already defined over here. So we're going to create one more, for example, if you have a value of 2, which will be, so we're going to add layers as much as we want. So in this case, we're trying to make this network scalable. So we can define a number of layers and just like put any number of hidden layers that we want. Okay, so I think that's clear. And the activation will be ReLU because we're dealing with some regression, and ReLU is usually the best. But again, you can change this if you want to see how it goes. And after adding some hidden layers, we're going to add an output layer, which will have a dense value of 1. So it's just a single node because we're trying to make a regression, and the regression it will try to output a single value. And then we're going to define the optimizer. In this case, we're going to define Adam, and the learning weight of the network is basically a value that tries to estimate how quickly you descend your gradient. So since you're trying to make a gradient descent algorithms that you look at the loss and try to minimize it, the learning rate basically dictates how fast do you minimize it. So if you go for very high values of the learning rate, it will kind of like it will achieve the bottom fast, but it will fluctuate a lot. So you have a lot of fluctuation. If you go for a slower learning rates, for a lower learning rate, you manage to, even though you manage to go to the bottom of the gradient, it's lower, you will manage to have a much more precise result. Okay, so then we will compile the model. Again, it's the same way that we did the CNN. We're going to define the optimizer, which will be the Adam optimizer. We will define a loss, which in this case will be the mean square error, and that we also define the last class. And then I'm going to print some metrics, which will be the MAE, the mean average error. And again, I'm going to print the mean square error just because I wanted. And okay, so it looks good. We have a lot of hyperparameters over here that you can change, and we're going to try to change them later. So we will use the mean average error, the mean square error sorry, just the mean square error as a loss. And you have some difference between them. So I wrote over here that the main difference between these two is that the MAE is usually more robust with data with outliers, while the MSE is usually better for converging as we move closer to the loss minima. So in the case of, since we don't have a lot of outliers, we're going to use the mean square error. And a decision has to be made to like which one of these. Yeah, okay. And sorry, we just wanted to tell that we can call them L1 and L2 match losses. So it is the usual name that we're going to see in regression problems is L1 and L2, but it's the MAE and MSE. And there is no superior loss. Each one has its pros and cons depending on your data set, and you need to choose them carefully. Okay, so let's, since we, where is the, oh, okay, so it isn't here, no, but I don't know why there's missing a cell over here that should build the model. And then we're going to, so I needed to call the function build model, and then we're going to train the model. So the model will be trained by passing the training data, the features, and then the features and the targets. And we're going to define a validation data. Since we are basically using just training and validation in this case, the testing, training and testing, the test set is going to be the validation set, will be the same thing. And we're going to define a number of epochs. In this case, will be 50. and we're going to define a batch size of 120, and a verbose just means to print things out. So if you verbose equal 2 means that you print each line, each epoch, and verbose equals 0, for example, will hide all of the you hide these outputs, this printing process. Okay, so we will print this. So it will go through all of the 50 epochs, and after finishing training the data, we can now evaluate the results. So in the same way that we did before, we had some neural networks prediction. So let's use the mean square error and the R squared metric. I could again just like use the evaluate function, but that would only give me the MAE and the MSE. I wanted also to calculate the R squared. So I'm going to predict. So the first thing that I'm going to do is to predict the output for the test set, and then I'm going to transform them back, because the output is going to be scale between 0 and 1, and I want to compare like with physical values. And so I'll calculate the R square, which obtains a value of 0.98, and the root mean square error, which obtains a value of 0.093. And you can see that 0.98 is already better than even though it's a very simple network, it's just a little bit better than the results that I had yesterday with the random forest and the XGBoost. Okay, so this begs the question: can we make this better? So can we make a better network that fits to solve this problem? And so we're going to talk about I think something that a lot of you might be interested, which is hyperparameter optimization. So hyperparameter optimization is basically when you change the hyperparameters in a way that you see different results, and then you can choose which is the best hyperparameter to use with your model. So in this case, we will do what is called a grid search. So we will define a grid. So each hyperparameter will have different values that it can be that it can possibly have, and then we're going to iterate through those values to see the performance of each one of them, and then try to find a solution that we're happy with. And depending on your model, hyperparameter optimization in this way, using grid search, can take some time, but this is the simplest way for you to do. But there are a lot of different ways for you to do optimization. One of them is a library that I wanted to talk about that is called Optuna. So I'm not going to talk about it now because you would require a class just about Optuna itself. But it's a library that it was developed for machine learning use that tries to make it it's much more efficient for you to optimize your hyperparameters. So it has things like, for example, so like early, like it kills the network if the results are not converging, for example. So if you're comparing different hyperparameters, like one combination of them, you see that, for example, the loss is much worse than every other one of you that you try. So Optuna is going to kill the network before reaching the last epoch. So it's much more efficient. But if you're trying to optimize your models, I really recommend you check it out. So there is a lot of documentation out there on how to use it. Okay, so let's try to first find the best number of hidden layers that we want for a model. So remember that right now I'm just using 2 hidden layers. So let's see, for example, for 2, for 4, for 8, and for 16 possible hidden layers. I'm just choosing a power of 2 because it's usually better if you choose powers of the numbers that you want to work with, because then it's easy for you to like estimate where is the best value. So for example, if I see that like 80 and 16 had the best results, but they were like tied for the best results, maybe the best result is somewhere around here. So like maybe it's like 10 or 12, and I can try different parameters by having like this power sequence. It's usually a better way to do it. And so we're going to define the possible numbers of layers, and then I'm going to just create a dictionary called MSE layers just to store the MSE of each one of them. And so to try to find the best number of layers, I'm going to go through this list, and each time I'm going to go through this list, we're going to use kind of like that machine learning universal workflow all again. So each time that I loop over here, I'm going to first of all clear the. I'm going to use this function called clear session. It's basically going to, so every value that, for example, Keras has stored in the memory is going to clear it out. So it's basically going to compile a fresh new model, and there is no problem, for example, with if you have lower memory in your system, it's not going to clutter a lot of memory. So you don't actually need to do that because of Google computers are pretty good. But in the case of, you can see the amount of RAM and disk that you're using. But if you have like a lower end computer and you're training a very big model a bunch of times, it's usually good for you to include. And I want to include it just so you can see its usage. And then we're going to build the model. So we're going to use the build network function. By defining the X string, by giving it the data that we have, and then giving the number of layers that I want. So remember that there was a parameter for the function, and now we're going to give the number of layers that I want, and each time that it builds this network, it's going to build a different network based on the number of layers. And then we're going to train after building the model, which inside of this build network function, it will already compile the model. Then we're going to train the model, which by using the fit function. And in this case, I'm going to increase the, I'm going to use 50 epochs just to see how it goes, a backside of 128, and a verbose of 0, which means that it's not going to print the outputs, just so it's so it's easier to read. And then I'm going to predict for the test set, we're going to predict the metrics. In this case, I'm going to predict the mean square error of the model. And finally, I'm going to print the results for each one of those layers. I'm going to print the results that we have. And you can see that for in this case, in for analyzing the number of errors, you can see that we have like so results for the number of errors. We have the like 2 for 2 layers. We have like this MSC, and then for 4, and then for 8, and then for 16. And you can see that we want the lower MSC. And in this case, so it's printed, it ended up with the 2 hidden layers, because whenever you run this, it's always based on the Cs that you run. So for example, I think that later I also reran this notebook, and the best number for layer was 4. So it's quite a like they're very close. For example, what I want to say, this MSC means that the network's managing to fit so well the problem that it doesn't really change if you choose like from 2 to 4 to 8. But in this case, I'm going to choose the 2. But you can see that I think later I defined it as 4 just because when I ran it, probably the seed ended up with a 4 as the better. And then we're going to also run for the best number of neurons. So we're going to study the possible values that of neurons for each one of those layers. And I'm going to use 32, 64, 128, and 256 for the number of neurons. And again, I'm going to do the same pipeline. So the same pipeline that I used before. So it's going to clear the session. It's going to build a model based on and it's going to pass a number of neurons that I defined before. It's going to fit the model and then predict some metric that I want. In the case, the mean square error again. And let's see what we have here. So the MSC results of the neurons was for 32, for example, we had this, and you can see that the best one was 256 neurons. And okay, so I define over down here the best neurons and the best layers to be used later. And again, just to tell you that when I ran it, the best layers was 4. And if you run it, maybe the seed will be different, and you will have some different best number of layers. Okay, and what can we do with it? What can we do since we have that information? One of the things that we can do is to use k-fold cross-validation, which is something that Laerte talked about yesterday, which is a way for you to better estimate the error of your network. So the idea of the k-fold cross-validation, I think this image represents it really well. So if you have all of your data, so you have all of our data over here, for example, you want to, for example, you take your training set, and then you divide your training set into different amounts of folds. So in different folds, parts of the training data. And then you will run your model many different times. In this case, I'm going to define five folds. So I'm going to run my model 5 different times. And each time that I do run my model, I'm going to use one of the folds for validation and the other ones for the training. And then I'm going to look at the validation folds, for example, and see what was the metric, the final metric of the model. And then I'm going to do that for split 2. And in split 2, I have a different data set. Every single galaxy that was in the validation set, for example, in split 1, now is in the training set, and the validation set is completely different from the one before. And so in this way, after looking at the metrics for all of the 5 splits, you can have a better idea for like how your model is performing based on, for example, on the epoch. You can just have a better idea of your model. So for example, if I ran a k-fold cross validation for estimating the hyperparameters itself, maybe, for example, 4 layers would be the best, or maybe 2 would be the best. The only way to really know is to, well, not the only way to really know, but a better way to have a grasp of the idea is using k-fold cross validation. Okay, so how we're going to do that is that we're going to define we first need to set the fold, the k, basically the number of folds that we want to use. In this case, I'm going to use 8 folds. So it's going to divide since we have 85% of the data for training, it's going to divide the training sets into 8 different folds. So it's going to be like 75% for training and 10% for validation in each one of the folds. And I'm going to use the k-fold cross validation, but there are different methods for analyzing the performance of the network. One of them, that Laerte told us before, was the leave one out. So the leave one out is like a kind of k-fold cross validation in which the number of folds you're going to use is the same number of data points you have in your training data. So for example, if I have like 100,000 galaxies in my training set, then I'm going to have 100,000 folds. So the idea is that each split that you run, you leave one of the data points out. That's why it's called leave one out. And then you're going to train with all of the other, and the next split you're going to leave the second value out, and so on. And there are others, shuffle split, for example, but k-fold cross validation, it's really good. It works really well. And so in each one of those folds, what is my what I'm going to do is, first of all, I'm going to separate a new training and validation set. So that's the first step of like entering each fold. And I'm going to compile and build a new fresh model. And then I'm going to fit the model and then save the history of the model, which is going to give me information about the loss, how the loss is changing. And in each fold, I'm going to run for 100 epochs, so we can try to understand the performance of the network for a higher number of epochs. So to see if it converge, for example, in the case of 100 epochs. Okay, so how we're going to do that is we're going to use the a k-fold coordinate. We're going to use the sklearn.model selection fold. So this is a function from sklearn itself. So it will we will be using that over here, and then we're just going to define 2 variables to store the numbers. So the first thing that is going to do to start the k-fold loop is to separate the k-fold. So it's going to each time that it runs this line of code over here, it's going to take a different train and a different validation set from these folds. So I define the number of splits, and then I split. I want to split this data over here, the training data and the training targets. Sorry, the training. Yeah, I think you get the idea. And so let's clear the session, remove the clustering data. Then we're going to build the model, and then we're going to print, like just for you to see, because I don't want to, since I'm going to train a lot of different folds, I'm going to use a variable 0, so I'm just going to not print the output of the model itself. just because it's going to look bad. And so, and then I'm going to save the history of the validation, and I'm going to do that like a lot of times, and each time that I do, so I'm going to do that for 8 times. And after I'm finished, so this all histories list over here has the history of each one of those um, folds. Okay, so what can we do with it? So one of the best things that you can do with k-folds is to look at the loss history. So we're going to look at how the loss changes for each epoch. So it's basically the same idea as like this information over here. So in this case, we have like when I ran without variables, like variables 2, that it prints the output for each epoch. You can see that for each one of the epochs, for example, epoch equal 1, you have some like the loss, and then for 2, and then etc. And if you plot this graph, what will happen? And this is the idea of looking at the k-fold cross validation. So we're going to plot over here. So this is we have the validation loss, which is going, oh, sorry, just to explain how I managed to gather that information. So it's going to come from the history. So each one of the histories of the folds, you can call the loss. So the loss of the fold itself, of the model, and then it has you need to ask it for like what is the epoch that you're talking about. And okay, so we're going to run this for the like we're going to get information about the 100 epochs that we ran. And so after plotting these results, we will have something like this. So this is in the x-axis is the number of epochs, in the y-axis is the number of is the loss of the model. And remember that in this case, the MSE, we want to make the lower the better. That's the idea. And so if you look at the blue line is showing you the training loss, so the average of the training loss of the model. And the orange line is going to be the validation, the average validation, and then the color behind it, it's the maximum and minimum value. So it's basically just for you to have an idea of the scatter of the training loss. And you can see that I'm going to only plot this after like 10 epochs, I think. Yeah, so 10 epochs, because if you try to plot it before 10 epochs, it's going to be it's going to be very hard to see. It's going to go up and down and up and down. And then it's just important for you to look at like a fixed number. So for example, from 10 upwards. And one interesting that you can look at this picture is to find the turning point of the network when you have like overfitting and underfitting. So you can see in this case, for example, that like the validation loss and the training loss are walking like side by side, each one. And the validation loss, the training loss is always going to decrease. So the blue line is always going to go down. Is always going to decrease. While the validation loss, there is one point in which it starts to increase. And this is the point that we want to find to maximize the best results of our model. And you can see that in this case, the validation loss is not increasing. That's because we probably chose a lower number for epochs. So for you to see like a neural network, like the turning point, you need to run this network for like thousands of epochs, like 2,000 epochs, 5,000 epochs, and this can take a lot of time. So that's why I decided to just run for 100, because if not, the notebook would take like a couple hours for you to run. So yeah, so that's one of the interesting things that you can try to look in these plots over here. And okay, so in like a best case scenario, when you have usually if you train for in the case, for example, for a project, if you train this for a very long time, you see the turning point, and then you can find the best number of epochs that you can run your model. And once you found the best epoch, you can train your final model. So using your whole test data, because remember, in the k-fold model, we are separating the data. We are separating into folds. So we're taking a part of the data and leaving out and we want to give the model the data when we train the final best model, basically the model that you either be applied to like some real data for whatever application you want to work with. And okay, so we're going to use this. You're going to go through the same process that we did before. So erasing the memory data, then building the model, then training the model, and then we're going to fit it here, and then we're going to print the just a message, and then we're going to print some metrics. So we're going to print the R square and the RMSE. So and then we're finally going to predict I'm going to plot the predict plot, which is the same that we show in the last week. So we have the targets on the y-axis and the prediction on the x-axis, and yes, you can see that the plotting is sorry, the prediction is doing very well. And I think that's it. That's what I wanted to show you. I know it's a lot of things, but I want to show you, like, just for you to have a general grasp of the how to utilize CNNs, how to utilize feed-forward neural networks for your classification, or maybe for your regression problems, whatever you want. And we left you with an exercise. So we're going to use the same data set that we gave you yesterday, which is a photometric redshift data set. So basically, we want you to estimate the photometric redshift based on the S plus magnitude. And so the data set you probably already have, but if you don't, you can again download it through here. And we want you to utilize some kind of neural network to estimate the photometric redshift, and then we want you to change the hyperparameters and see what happens when you change it. And you can use k-cross for k-folding cross validation and whatever you want. The idea is just to be very broad on what you can do, because like this is just a preparation for your project. So it's just for you to have much more freedom to what you can do and what you want to do. It's just to give you a general idea of what data set you can use, which is this one. And okay, I think that's it.
Questions for Vitor?
Hi.
Hi. Sorry.
Yes. Is it possible to use this grid search and cross validation in the case that you have a huge neural network? I mean, like a convolutional neural network with, I don't know, 6 encoders, 6 decoders. Maybe it will take a long time to search. And in the case that you cannot use it, you have to do it by hand. I mean, you have to try with different hyperparameters like learning rate and see the results, or there is an efficient way to do it?
So I think there are two questions, right?
Yeah.
So like the first question, if you can run this for like a very large network, and yes, you can. You're just dependent on your own like computing power, what you have available to use. Like the bigger the network, the more complexity you have, the more you take to train. But in this case, for example, it takes quite some time to train each one of them. I think it takes like about 5 minutes to train each model. Even though it's quite quick, it starts adding up. So for example, for 8 folds, it becomes 40 minutes you need to wait. And like if you want to leave one out, it's not possible, because it would take like days to train.
Yes.
But in the case of like a more complex, in the case of convolutional neural networks itself, they can be faster than the feeds forward, just because of the nature of GPUs and how they make the predictions. So in this case, for example, you could see that the convolutional neural networks took about 2 seconds per fold when using the MNIST data set. So maybe, for example, in your case, if you don't use even though your model is very big, it doesn't necessarily means that you take a long time to train.
Okay.
And for the second question, if you is about the hyperparameters, right?
Yeah.
And yeah, it's quite something that you need to, it just by working out and having a better grasp of what hyperparameters are good, for example. And we usually only work with powers of 2. So then it's not like a rule. You can change this value, but it's better for, like, it's just a common thing in the industry. And so if you know which hyperparameters you have in your model, for example, the number of epochs or the number of neurons that you want to change, the number of layers, you can change them however you want. You just need to set like a lower bound and an upper bound and define how you're going to go for that.
Okay, and another question. Here you use TensorFlow, I mean, you use Keras in reality. But if you use PyTorch, maybe can you have different results, very different results? Maybe the optimization can be better than in TensorFlow due to different implementations.
Yeah, I think that so they have different backends, like how they do the calculations are pretty similar, but they can have some small differences. And I'm sure that if you ran, for example, this problem with PyTorch, you would get some slightly different results. But I don't think it will be such a big result for a problem like this. So a problem like the one that I'm showing you, it's probably not going to have a very high difference. But if you're having a problem, like if you're going in the scale of like very big companies, so if you, for example, are trying to train one of the train networks that I like to showed before, like the competition, if you're going for a competition or something like that, then yes, you're going to maybe see a lot of changes on how each one of them work. Because, for example, PyTorch gives you a lot of freedom when choosing the hyperparameters, and you have a lot of freedom over your model, and which is not something with Keras itself. But you can try to do with that with TensorFlow. But yeah, you're going to see some difference if you. It's not a lot, but you're going to see.
Okay, thank you.
Hi, Victor. Thanks for
Hi.
the class. Regarding the hyperparameters, when you search for the best ones, you fixed one and you search for the other and the other way around. I mean, these parameters are always independent one
No,
from the
no, no, no,
other.
no.
I mean,
They can be. There is a dependency on them. So, for example, in this case, I'm assuming the best hyperparameter is like the 2. So when I built my network over here, I defined that the best hyperparameter for layers would be 2, and the best hyperparameter for neurons would be 128. But that's
right.
not necessarily true. I just did that because you would actually need that. That's I think your question. You would need to see the correlation
Well, the
between
combination,
the
exactly. Yeah.
combinations of them.
Yeah.
And yeah, that's totally
That's
correct. But the
okay.
problem is that you would, for example, for four hyperparameters in each one of them, we now have 8 possible models, right?
Yeah, of
So
course.
4
It's
in each
more
one.
expensive.
If you do the combinations, you have 16. So if it already takes like 1 hour for you to train this notebook, you now take 2 hours, and so
No,
that's
no,
that's
I
the problem.
understand. Yeah.
If you use, that's what I wanted to talk about Optuna, because if you're using grid search, which is the thing that I did over here, it's going to be it's not going to be so efficient. But if you use Optuna, yeah, that's really good. So this library can manage it does the combination. So you just like pass the possible values that you want, for example, the number of layers or the number of neurons, and then it's going to try to do all of the combinations. It's not actually going to try all of the combinations. It's going to try to like balance it out. For example, if you have similar combinations and you see like the one of them doesn't work, the other one probably doesn't work too. And so it tries to optimize the results by using in that way. But
Great.
yeah, you're
Thanks.
totally correct. There is a correlation.
Thank you.
More questions? No?
A question, Vitor, how long took to run this
The notebook
document?
entirely.
Yeah,
Um,
about more or less.
yeah, I think it took so the CNN part was very quick, so it took like less than 5 minutes, I don't think, like 2 minutes to run the whole thing. And the thing that took a lot of time was this hyperparameter, so it took like about 40 minutes per block of, sorry, 40 minutes, no, so 20 minutes per block over here, so like 40 minutes overall. And then it took some time in the K-fold, so it took about more 40 minutes. So about 1.5 hours, that's the idea for the whole notebook, if you want to. But I don't recommend like running the notebook itself. You already have the results. It's stored in the notebook itself. You can see the results. So I would recommend if you to try this with your own data, but not like running what is already done.
Any other question? And Laerte, what kind of people win these challenges? This has the kind of profile like engineer and softwares or something like that? Okay. Okay, if there are no more questions, I will change to Spanish. Yo quisiera agradecer primero la presencia de todos ustedes, el interés por el curso. Creo que es importante empezar a introducirnos en esta clase de temas porque me parece algo que se nos está escapando, o sea, que se usa mucho a nivel mundial y creo que acá en La Plata me da la sensación que se nos está yendo. Entonces es bueno por lo menos introducirnos a través de un curso introductorio y ver si lo podemos mantener a futuro con algún tipo de actividad y un segundo curso quizás. Quisiera agradecer a Laerte y a Vitor por haber venido a darnos este curso. Voy a cometer una infidencia, Laerte estuvo a punto de no poder venir por un tema de salud, pero por suerte se repuso y lo tenemos acá, por eso insisto también de que lo aprovechemos. Ahora tenemos la semana que viene todavía 3 días de ellos acá en la facultad, así que me gustaría insistirles sobre que interactúen con ellos, tanto Laerte como Vitor se manejan bastante bien en portuñol,